Hello, Physics 30. Welcome to EMR Chapter 13, Lesson 3. We are going to get into the reflection and refraction of light, depending on what it's entering and exiting. So, for example, you've seen this before in real life. You take a pencil and you put it behind a glass of water, into glass of water. It looks like the pencil is broken. You've got, Dr. Sheldon Cooper here. He shows this here, right? Which is kind of a cool idea of refraction, right? And we have refraction as well, right? If we're looking for something in a swimming pool, if you throw your spear at where you see the fish, you'll miss. But if you aim below the fish, then you generally will get a easier target. Not that I expect any of you guys to go spear fishing anytime soon, but if you do, that's kind of a little thing that helps. Okay, you should have already done this anticipation guide. If you haven't, it'd be a good time to do it before you watch this lesson, but I mean, you'll still be just fine. Okay, this one here, it may or may not work in your Chromebooks. I've tried it on my Chromebook. It did work, but I'm not sure if mine's different. I like to install stuff differently or not. If you do, just go play with it a little bit. Look at the difference in reflection and refraction. Okay, and notice this n value, okay, changing. N is basically how dense an object is and how much it changes the way light behaves when it enters or exits it. Okay, and that's pretty important. There's also a critical angle and stuff like that. All right, come on. So first thing we're going to do is reflection of light. The reflection of light is relatively easy. It's basically the angle of incidence equals the angle of reflection. Okay, all right, but it's always going to be measured from what's called the normal. So whenever you have a surface, okay, whenever you have a surface, doesn't matter if the surface is this way or this way, there is, when light comes to hit it, the angle in which it's hit is measured from what's called the line of normal. The normal line is perpendicular to the surface, right? So it's perpendicular to the surface. So if the angle comes in, it's going to bounce off like that. If the light comes in this way, it's going to bounce off like that, right? And what this is saying is basically the angle on either side of these, right? So the angle here and the angle here are the same. The angle on this side of the normal and on this side of the normal are the same. I don't know why I drew that sideways, but guys get the idea. So the normal is basically perpendicular to the surface. It has this idea of normal force, right? Normal force is perpendicular to the surface as well. So the normal line is perpendicular to the surface. All right. So that's the law of reflection. All right, it holds true when the surface of E is even, right? It's a nice blue line there. Okay, so it holds true when the surface is even, but of course, if the surface is rough, it doesn't quite hold true. So we're usually going to talk about mirrors or glass or things that are reflective, right? Things that are reflective are generally going to follow this law of reflection. If they're, not, for example, like you can't really reflect something off a rock, but we can reflect something off of sand. Or off of glass, which is really sand, which is a bunch of tiny rocks. I know it's confusing, but if it's basically a level, even surface, it reflects good. If it is a rough surface, then it won't reflect, and this law kind of breaks down. All right, and you can see that here, right? That's a nice little surface; it reflects well. This is an uneven surface; it kind of just reflects randomly, and we don't really see any kind of reflection. All right, so we're gonna have to use some angles and stuff like that to figure this out. Okay, so two plane mirrors form a 70-degree angle as shown below. What must the angle theta be measured from the surface so that the final reflected ray is horizontally parallel to the initial surface, right? So what angles result in this is basically what's asking us. What angles result in this motion? All right, so we have to basically do some geometry here and understand that the angle between the parallel lines and the intersecting line is the same. So if I look, basically what I've got here is I've got what I'm going to consider two parallel lines, right? Two parallel lines. And they've got an intersecting line. All right, and so we'll call this intersecting line here is this green one, or is this one right here. So this is an intersecting line. All right. So what that tells me that is if this angle here is 70, since it's the same line is on this parallel line, then it must also be on this parallel line. So that tells me that this must be 70. So this angle here is also 70, okay? This is something you learned in Math 20-2 20-2 pretty explicitly about geometry and stuff like that, okay? But it kind of makes sense, right? If these are parallel lines, right, like I said, these two lines are parallel, so this line and this line are parallel, and you have one line intersecting them, the angles Wix makes must be the same. Okay, so that's 70. Good. All right. So if I think about it, due to the law of reflection, then this angle must also be 70. Okay, this angle must also be 70. Right? Now you're going to say, you just said you have to measure from the normal, measure from the normal. Right? If I measure from the normal, right? If I measure from the normal, then basically from here, right, both of these angles are going to be 20, which tells me that this is 70. All right, so that's 70. Now I can continue this, and I see this is a triangle. 70 plus 70 is 140, and so there's 40 left, so this must be 40, which tells me that this must be 40, because to measure to the normal, 50 and 50, so 40. All right, so the answer to this question is what angle must it be? Well, it must be initial angle of 40. Must be initial angle of 40, right? And so you can figure out the rest of these angles, but it's based off this idea, okay? So that's just using geometry to kind of figure something out, all right? That's about as hard as reflection can be. You can use practical use of reflection. You can check out this periscope, but periscopes are relatively simple idea, and they're used predominantly in submarines, or what we're going to see them in, right? And so it's this kind of shaped object, right? And what you have is some object or some light source. Okay, you have some kind of source, and then you have an eye, you have an observer, right? Okay, you have an observer, and what you do is you basically have two mirrors in here, and any light that comes in is going to hit this mirror, bounce down, and then bounce over. It's basically two 45-degree angle mirrors, two basically 45-degree angles. And so what we can do is we can actually use it as a periscope. Remember, this is using submarines, right? The thing you see in submarines, those are periscopes. All right, it's just a way for us to see using two mirrors. And so what's interesting though is that your eye is tricked. Your eye is tricked. What your eye actually sees when you're doing this is your eye actually thinks that you're just looking straight out. And it's a very interesting phenomenon, is that your eye thinks you're just basically looking straight, even though you're actually looking at light that came from up here, right, with the angle. So you actually are tricking our eye. Okay, and this has been used. You have basically these guys here. We're at it looks like a baseball game, but I can't tell for sure. They couldn't see, so they used a periscope setup. They used cardboard and some mirrors, and they actually can look and they can see over all the stands. You can also watch this video on how to make a periscope. It's kind of fun. All right, so that's reflection. Reflection, relatively easy. Comes in at an angle, bounces off an angle. That's all simple. Alrighty, so now we're going to talk about refraction of light. Okay, so imagine you're driving down the road and see a big puddle on the side of the road, and your mortal enemy is walking the sidewalk beside the puddle. What is your first thought? So you go to hit the puddle at an angle, but only one of your tires goes in the puddle. So you've driven before, right? What happens when one side of your vehicle hits something thicker, right, like a puddle, than air? It slows that side down. And so what happens to your vehicle is that side gets slowed down and you get pulled into it, right? So you're going to get pulled into it. So if your right tire hits the puddle, you're going to get pulled right. Well, the same idea happens with refraction. So refraction is usually when we're going from between two different mediums, right? So we're going from air to glass, or glass to water, or air to water. Okay, and so you sometimes basically what you're going to see is that when this happens is that when the first part of the angle hits, right? So when the first part of the ray hits, it's going to get pulled in. Then the second part's going to get hit, and it's also going to get pulled in. So basically what's going to happen is you're going to get pulled in towards the normal. All right. What's important as well is that the frequency does not change. wavelength can change, and so can velocity. So velocity and wavelength must also change. All right, and so light kind of changes what's going on. So frequency remains the same, right? It's gonna keep hitting at the same amount of time, but the wavelength can change, spread out or get narrower. All right, and so that's what refraction does. Is it actually can change velocity. So we know the velocity of light. The velocity of light is 3 times 10 to the 8. But you'll notice anywhere you say that, it says in a vacuum. Definitely spelled that wrong, but in a vacuum, right? How do you spell vacuum? I know. There you go. What a weird word. Okay, in a vacuum. All right. But you'll notice that if it's in air, it'll slow down. Usually still in air, we're going to say 3 times 10 to the 8. But if we enter glass or if we enter water, the velocity does slow down ever so slightly. Okay, so we have to deal with how does this work, right? So how does this work and how can we use this to help us out? So what's interesting is this is really good. If you can get this, if you can't, what this shows basically is that the light's going to come in pretty far apart. But when it enters this medium, right, this more dense medium, what's going to happen is it's going to slow the first one down, and then the second one has a chance to catch up. Then it'll slow down. So they actually end up getting closer together within the actual medium, right? Then when this front ray leaves the medium, it actually gets a chance to space out again. So these will actually space out once it leaves again. And so the velocity changes and the wavelength changes. The frequency stays the same, but as it enters, right, as we enter, we're going to slow down. Okay, we're going to slow down. And then as we leave, we're going to speed back up. All right, that's a crazy thing about light, is it just inherently speeds up, right? Inherently speeds back up once it leaves the medium. And so basically the velocity over here and the velocity over here are exactly the same, okay? That's kind of it, all right? So then we get into this concept of, okay, we got to talk about like what is actually happening and how do we compare these things. So what we do is we have this idea of n, all right? So n is the index of refraction of a medium. It's unitless, all right? And so the speed of light in a vacuum is 3 times 10 to the 8. And so we say about the speed of light of air is 3 times 10 to the 8 as well. So we say that for air, n equals 1. All right. For objects that are more dense, the higher the n value. And you can see that when you look in here, right? The more dense the objects, the higher the n value, right? And so basically the higher the n value, right, the slower light moves in it. All right, the lower the n value, the faster. Now, n is always going to be greater than 1, okay, or equivalent to 1, I guess, in this case, but it's always equivalent or greater than 1 because it can't go faster than the speed of light. It can't be less than 1. All right, the good news, you don't have to memorize this. You just have to understand what n really is, right? N is just basically a measurement of how fast light moves in each medium. All right, you'll notice that on the back of your formula sheet, it says the index of refraction of air is always 1. Okay, so when we basically have this, if you change the index at some point, the more you increase this index, the farther this will get away. But you'll notice that as it goes into the medium, it's going to bend towards the normal. As it leaves, it'll bend away from the normal. So over here, if you think about normal, right, it'll actually bend away from the normal, okay? And so you have all sorts of weird things like apparent bottom and actual bottom and weird things, okay? So when we're going to calculate it. All right, so now we're going to calculate it using this equation here. Now, this has got 3 equal signs. 1, 2, stop. Okay, it's got 3 equal signs. 1, 2, 3. Now, whenever you're doing this, you don't have to do the whole equation, right? What you're going to do is you're going to use based on what's given to you. All right. So if you're given the angles and the n values, then you'll just use these ones, right? If you're given the velocity and the angle, then you use just the velocity and the angles. right? If you're using the index and the wavelength, right? And so you'll notice is that you can kind of just pick and choose, but in order to use this equation, this is just like the sine law, it's actually the sine law, is you have to have 3 pieces of info and 1 missing, okay? So you always have to given or find 3 pieces of info, you'll have 1 missing, okay? The other thing I want to note is that for sine, velocity, and wavelength, it's 1 over 2. But for the index, it's 2 over 1. It's always 2 over 1. Don't mix that up. Double check your formula sheet before you add anything in, before you calculate anything. Okay, that's going to help you a lot. All right. So on the old formula sheet, it used to look like this. I don't know if you guys have the old formula sheet or not, but on the new one, it's got this just split into 2 spots, but it still means the same thing. These all equal each other. All right. So what's going to be interesting as you find is that if you're going from less dense to more dense, so from air to water, the light will bend towards the normal and slow down. If you're going from more dense to less dense, the light will bend away from the normal and speed up. All right. So for example, I have a ray of light traveling through air. So N1 equals, so that N is equal to 1 in that case, is in spot on diamond. Okay. At 2.42, it is at an angle of 60 degrees to the surface. What is the angle of refraction? Right, so I wrote down my N1 is 1, my N2 is 2.42, my angle 1, is 60, and the question is asking me for, not Q, angle 2. That's what it's asking me for. So we're going to go ahead and fill this out, right? So I'm going to say sine 60 over sine theta. Of course, use Q, use whatever you want, right? Angle 2, and N2 is 2.42 over 1, right? And so we can go ahead and figure this out. This is going to be sine 60. When I do this, it's going to end up being sine 60 over 2.42 equals sine angle 2. Don't forget to do your inverse sine at the end. So what does angle 2 equal? So we'll use our calculator. Sine 60 divided by 2.42. And then do inverse sine of that number. Make sure your calculator's in degree mode. And all right, so it's going to bend towards normal. So it should be less than 60. And the answer here is 21 degrees. So the angle 2 is 21 degrees. All right. So that's just using these kind of laws and stuff like that. All right. And that gives me the angle of refraction. Go to the next page. Okay, so we can have refraction go like this. All right, and we can have basically something enter and exit the same way. All right, so when the wave enters the medium, which way does it bend? Well, it bends towards normal. When it leaves, it bends away from the normal, right? And so we have kind of this different idea. Okay, so basically what's going to happen is a beam of light strikes one face of the window pane with an angle of incidence of 30 degrees. The index of refraction of the glass is 1.52, and the beam travels through the glass and emerges parallel from the other side. Okay, so find the angle of refraction for the ray in the glass. So what we've got here again is we've got an angle of incidence. So my angle 1, right? Angle 1 is 30. I know that my N1 is 1. My N2 is 1.52. And I'm looking for angle 2, right? So it sets up the exact same as the previous page, right, where I have sine angle 1 over sine angle 2 equals N2 over N1, right? And so I've got sine 30 over sine angle 2, which equals 1.52 over N1. And we just saw this on the previous page, so I'll just hit my calculator and figure it out. All right, so sine 30 divided by 1.52, hit enter, and then inverse sine that answer. And you're going to get an angle. That angle 2 equals 19.2 degrees. Okay, again, that's from the normal, right? So using trigonometry, we can then tell that if this is 19.2, then this is also 19.2. And it wants us to prove that when it emerges, it's going to be emerging parallel, which is the same thing. So now we're going to do the second part of the question, right? Where now I'm in the glass and I'm going out to air. So this is where I'm in the glass to the air, right? If I'm in the glass, I'm going to the air. All right, so now I know my original angle. Okay, my first angle is 19.2, all right? Don't round that number if you don't have to in your calculator. All right, then my N1, well, my N1 is now 1.52, and my N2 is just 1. Okay, and I'm looking for angle 2. I keep putting Q's, I don't know why. Looking for angle 2. All right, so notice again, the biggest difference here is that the N1 and N2 switch. So we're going to take the same equation that we used before, which I can just copy. Okay, I can copy that. You can't, but I can. All right, and I'm going to basically go into, well, I've got angle 1, so sine 19.2 over sine angle 2, but now these switch, right? This becomes 1. This is 1.52. All right, so now I'm going to do sine 19.2 times 1.52. And then inverse sine that. And when you do that, you're going to get that angle 2 equals 30. Okay, and if you didn't round it all, you would have got 29.99, which of course we round to 30, right? So that just proves that whatever the incident ray is, right? So if this angle is this, when it leaves, it will still have the same emerging ray, okay, the same emerging angle. Right, so this initial angle and this final angle are the same. That's all that's proving. Okay? Alrighty. So now we can get into a little bit more of a practical, realistic thing. Alright, so narrow beam of ultrasonic waves reflects off a tuner in the liver as shown to the right. The speed of the wave is 10% less in the liver than it is in the surrounding medium. How deep is the tuner below the surface of the liver? So just for easy sake, I said that, well, let's pretend that the velocity in the medium is 3, and I found the velocity within the tumor to be 2.7. I just times that by 0.9, right? So it's 10% less, or 0.9 of. Okay, and I know angle 1 is 50, all right? So what I'm going to do is I'm going to find angle 2, and I've labeled this. I've actually taken this little piece right here, and I've zoomed in, all right? So we're going to find angle 2, and then we'll go from there, okay? So this is sine. Sorry, I gotta zoom in, otherwise it's really messy. Angle 2. Alright, V1 was 3 times 10 to the 8, and V2 was 2.7 times 10 to the 8, because it's gonna slow down a denser medium, right? Alright, so we're gonna do that 3 times 10 to the 8 divided by 2.7 times 10 to the 8 is 1.1111, and then you're gonna take that and go sine 50 divided by that number and inverse sine that. Okay. Now remember, the way you'll know this is wrong, if you did something wrong, is if the angle is wrong. Okay, so it was an incident of 50, right? Which means that it has to be less than 50. So if you did it backwards, you get a number higher than 50, which doesn't make sense, okay? Because we're going from low density to high density, so we have to do this. So angle 2 is going to be 43.6. We'll go with 43.6 for now. All right. So I want to just show you what I did here. Is I basically took just this part, the actual in the tumor here. Now I know the total distance all the way across is 12, but I broke it into a right angle triangle. Why am I do that? Well, because right angle triangles are cool, right? And so what I figured out here is that now I know that this angle is 43.6. That angle there is 43.6. So how might I find this angle here? Well, we're going to take 90 and subtract 43.6, right? And so this is 46.4. So that angle there is 46.4. So remember, what is the question asking for? Well, it's asking for this. This is what it's asking for, is that length there, right? So if I look, I've got a right angle triangle, I've got an angle, and I've got the adjacent side. I'm looking for the opposite. And so I'm going to use tan, right? So I'm going to use tan, opposite over adjacent, right? So then tan of 46.4 equals x over 6. Solve it. X equals 6.3. And since it was originally measured in centimeters, we're going to have our final measurement in centimeters. So how deep is the tumor below the surface of the liver? Well, it's 6.3 centimeters, right? So this is super cool. So just by using angles and reflection and reflection and refraction and distances and stuff like that, we can actually find depth of a tumor without actually having to go in there with a ruler and measure it, right? We're just looking at the way things behave within these mediums, okay? Now what you do is you take this concept, but you program it into a supercomputer, right? Put it in a supercomputer or anything like that, and then it can automatically read these things. And that's how you get things like MRIs and all sorts of stuff like that, is you basically have this concept, but you're taking it to a whole bunch of level, and you're doing it millions of times in a row, right? The same calculation that we just did, but you're doing it a million times, right? You've got things that give off rays and things that detect rays, and it's very complex, but it's based off this simple concept of light entering and exiting different mediums and reflecting or refracting depending on what's going on, right? Okay, you can watch this video about why is the sun yellow and the sky blue. These are things that you probably have an idea of, but it goes into a little more of a scientific concept of reflection and refraction, right? Okay, so that brings us to assignment practice problems 4 to 16. Alrighty, good luck, you guys, and let me know if you have any questions.